Well, everyone, konnichiwa. It's wonderful to see all of you here today. I thought what I would do is tell you a story about why we invented CUDA and give you a perspective of some of the developments in the computer industry from my perspective. I started my career about 25 years ago. When I was 20 years old, I was designing microprocessors. And in the 25 years that I've been in the computer industry, the performance of the computer has improved 1,000 times. My generation of engineers contributed to the greatest improvement of performance of any kind in any industry in the history of humanity. 1,000 times is very big improvement. Now this is started with VAXes and Cray supercomputers, and it led to silicon graphics workstations, file servers, which led to the microprocessor, which led to clusters, which ultimately led to the invention of GPUs. And during this time, as the performance improved by 1,000 times, from a software programmer's perspective, the single best way to improve your performance of your product, which is software, is to do nothing. Just think. The best way to improve the performance of your software by a factor of 2 is to don't touch it. Wait 1 year, and it will automatically be twice as fast. If you touch it, if you reprogram it, if you refactor the code, if you restructured your algorithm, you might break it. If you break it, you will miss time to market. If you miss time to market, you will fall behind. So don't touch it. Put more and more software features every single year. In fact, this example that I've described is exactly the example of Photoshop. It is the example of Excel. It is the example of SAP. It is the example of every piece of software, in fact, that we know, with the exception of video games. Video games, you have to redesign it every generation because you need it to do more and more and more, and performance must always be good. Well, about 2 years ago, doing nothing became a problem because, as we all know, the microprocessor design that you are very expert in programming ran out of steam. Several problems. The microprocessor design depends on sequential processing of instructions. And the best way to make sequential processing of instructions faster is to run faster. Frequency. Instruction level parallelism is very complicated to extract, as you know. We can recompile, we can branch predict, we can do out-of-order execution, we prevent deadlocks everywhere. We try to increase the number of registers by doing register renaming. We tried so many new technologies, and the instruction level parallelism went from 1 to maybe 2.3. Meanwhile, the transistor count increased by a factor of 2050, only for a little bit more parallelism. And the reason for that is because it is very hard to find parallelism in sequential code, as you know. Instruction level parallelism has effectively hit a wall. The other wall, the second wall, because we know that the best way to improve performance is frequency, eventually the transistors are never off. The transistors are now always on. So now the transistor density, transistor always on, the power became very high. And when the power goes up, the heat goes up. When the heat goes up, transistor slows down. So you're fighting. It's almost like a motorcycle rider going 1,000 miles per hour. Even more power cannot make him go faster because the headwind is too strong. So you've hit a wall. Then there's the third wall. Because the CPU fundamentally is about sequential access, it requires the instructions, it requires the data to be in cache. Well, in order to do more complicated software, you need bigger cache. In order to have bigger cache, it makes the chip hotter. If the chip is hotter, it runs slower. Again, there's a new wall, too many walls. Every direction we looked was a new wall. And so what happened, as you know, the CPU performance started to slow down. And we as an industry decided that the best way to improve the performance is to give you 2 cores. Now 2 cores is really fabulous because one can run the operating system and the other one can run the program. Perfect dual-threaded machine. Every single PC in the world is at least 2 threads. 1 operating system thread, 1 application thread. The problem is, where is 4 threads? There are no 4 threads. Most programs are single-threaded. And finding coarse-grained parallelism has been very, very challenging. The industry now recognizes that the historical approach of programming is causing, and the historical approach of designing computers is starting to see reducing or diminishing returns in performance capability. And so the whole industry is looking for a new approach. There is a very good paper that I would recommend all of you read. It's written by Dave Patterson and his team of researchers at Berkeley. And as you know, that Dave Patterson was the, I guess calling him the father behind RISC is too strong of a word, but he was certainly one of the inventors of modern RISC technology. Dave Patterson and Berkeley did Spark. John Hennessy and Stanford did MIPS, as you know. And between the 2 of them, they've both come to the same conclusion, that sequential processing as we know it today and multi-core processing as we know it today has some very big challenges. So the question is, what's the answer? About 7 years ago, we were building a new generation of GPUs. Completely in parallel, we came to the conclusion that one of the most important things we can do for graphics, for CG, is to make graphics programmable. And the reason for that is because graphics is not science, graphics is mostly art. And if we can make our GPUs programmable, we can allow the artists to express their artistic capabilities in an infinite palette called a GPU. And so this programmable approach was very expensive. It was very scary. In fact, we made many mistakes making the GPU, which is a fixed function pipeline, to become a programmable pipeline. And we made it more programmable, and one day we included IEEE compatible FP32. Now we included IEEE compatible FP32 because it is the easiest format for floating point. If you're going to create a new floating point format, you might as well make it compatible with a CPU. It's easy to simulate, it's easy to test. Now we went to floating point because when you're rendering computer graphics, you want to have a very high dynamic range. When we introduced FP32, software programmers around the world thought that maybe we can use the GPU for a very fast floating point unit because we had so much floating point in our chip. And so they discovered GPU.